A galaxy can't send news faster than 299,792 kilometers per second. That ceiling is light speed, and it caps what can change. Here is the twist you feel every day without noticing. Limits like this quietly shape the entire story of reality. They decide which futures can exist and which collapse immediately. Today we tour those hard constraints from atoms to horizons. The immediate takeaway is simple. Change is powerful but never unbounded. Once you know the rails, the universe stops feeling random. A supernova flashes on the far side of Andromeda tonight. Your fastest alert still crawls space at light speed, never faster. That limit defines causality, the order that keeps effects sensible. It means signals have boundaries, so change cannot outrun information. Relativity nails the idea in place with geometry, not opinion. Space and time knit together, and paths through them have limits. Push harder with rockets, the fuel just adds more inertia. Accelerate near light speed, and time slows for your ship. Energy demands explode, while gains in speed shrink toward nothing. Quick picture, you are chasing a laser pointer forever. The beam never gets closer because c is unreachable for mass. That is the idea here. C is the universe's speed cap. It matters because every reorganization of matter needs messages to move. No message, no coordination, no change on large coherent scales. Mechanically, moving things transfer influence by fields, and fields propagate at c. Tug electric charges, ripples run outward at that same ceiling. Even gravity carries news at sea via spacetime disturbances. The famous LIGO chirps proved that with a matched arrival. In real terms, Andromeda sits 2.5 million light-years away. An SOS launch today arrives in 2.5 million years. Closer home, the Sun is 8 light-minutes from Earth. A solar flare's particles hit later, but its light says go. Bottom line, change ripples at sea, so the universe updates discreetly. Stand in a collider hall, magnets hum like frozen thunder. Out fly sprays of particles, yet ledgers still always balance. The hidden bookkeeper is symmetry, which births the conservation laws. In plain words, uniformity in nature locks certain totals in place. That matters because chaos without constraints would erase structure immediately. Keep the totals constant, and galaxies, atoms, and chemistry can persist. Here is how it works. Symmetry forbids some changes and permits others. Shift everything in space, and momentum conservation drops out cleanly. Shift everything in time, and energy conservation falls out necessarily. Rotate your system, angular momentum must stay the same. Break that symmetry, and allowed motions shrink or new forces appear. Quantum fields encode these symmetries as deep phase patterns in math. But the upshot feels simple, accounts close, every interaction must balance. For instance, 2 protons enter with total charge +2. After smashing apart, fragments leave with total charge still +2. At the LHC, trillions of events respect that equality. Another number, neutrinos, carry away momentum to keep sums exact. Miss that invisible momentum, and detectors would accuse nature of theft. Common mistake is thinking conservation blocks change. It only shapes roots. You can rearrange energy between light, motion, and mass within totals. You can pivot momentum between particles, but not create it fresh. Net result, symmetry writes the rulebook, and conservation enforces the bookkeeping. Steam fogs a porthole on a deep space engine bay. Heat wants to spread, and it never stops wanting. That restless push is entropy rising, the arrow we all feel. Entropy, in one sentence, counts how many microscopic arrangements are accessible. Higher entropy just means many more ways to be disordered. This matters because usable energy is the currency for doing work. When entropy climbs, less of that energy remains available for tasks. How does it work? Tiny collisions scramble energy into diffuse microstates. Thermal gradients flatten out, so directed motion becomes random jostling. Engines feed on temperature differences, and their feasts always leave crumbs. No device can return every joule because the spread is inevitable. The best you can do is bounded by Carnot efficiency. With a hot side and a cold side, losses are fixed. For instance, imagine a Dyson swarm sipping starlight. The star sits near 58.0 Kelvin, while space is 2.7 Kelvin. That setup yields a theoretical efficiency of about 99.9%. It sounds perfect, but losses still compound over immense cycles. On human scales, a laptop erasing bits dumps heat by design. Landauer showed each erased bit costs kT ln2 energy. At room temperature, that is around 2.8 zeptajoules per bit. multiply by billions, and waste heat becomes a planning constraint. So remember, entropy limits efficiency, so every process pays a toll. Gas falls inward, heats up, then fights to escape as light. Gravity pulls harder, but light pushes back with surprising force. The tug of war sets hard ceilings on how fast things grow. The Eddington limit states brightness cannot exceed gravity's pull on gas. That rule matters because cosmic engines scale by how they feed. If radiation shoves gas away, accretion slows and growth stalls. Mechanically, infalling gas compresses, converting potential energy into radiation pressure. That pressure acts outward on electrons, dragging ions through Coulomb coupling. When outward push balances gravity, inflow becomes throttled, not halted. Black holes respect this balance, despite light not escaping their horizons. Their disks shine, and that shine punches outward against fresh fuel. Quasars at early times needed steady feeding near this ceiling. Here is a number: the Salpeter time is 45 million years. That is the E-folding time for mass growth at the limit. A black hole doubles repeatedly on that clock if fuel persists. For instance, a seed at 100,000 suns reaches a billion quickly. It still needs a few 100 million years, minimum, under ideal supply. If feeding spikes brighter than allowed, gas peels away into space. Jets and winds carry momentum, and the galaxy feels that feedback. Rule of thumb: gravity invites growth, radiation sets the speed limit. So the picture is, horizons exist, but growth throttles long before them. There is a silent current, galaxies drift with the stretching fabric. Expansion is not motion through space, it is space increasing everywhere. Put simply, distances grow because the metric changes. This matters because stretching space edits who can influence whom. As the scale factor grows, comoving neighbors slide beyond communication. In general relativity, the universe can expand from its own stress. Dark energy accelerates that expansion, making distant regions accelerate away faster. Light leaving those regions stretches too, increasing wavelength while losing punch. Redder light carries less energy, so influence weakens with every year. With numbers, H0 sits near 70 kilometers per second per megaparsec. A galaxy 1 megaparsec away recedes near 70 kilometers per second. 10 megaparsecs away, that becomes 700 kilometers per second. Push far enough, and recession beats light's attempt to catch up. There is an event horizon today near 16 billion light years. Light emitted now from beyond there will never reach us. Meanwhile, the particle horizon sits near 46 billion light years. That horizon marks the farthest light that could have arrived. Common mistake is calling this a speed limit violation. It isn't. Nothing outruns light locally, the stage itself is changing underneath. Bottom line, expansion writes a hard boundary on future cosmic connections. Peel a massive star like an onion, shells glow and churn. Each layer burns a fuel, and each fuel sets a schedule. That schedule is a constraint because nuclear physics loves balance points. Binding energy peaks near iron, so fusing heavier costs extra energy. That rule matters because stars cannot just build elements without payment. Fusion past iron demands input, so cores stall and collapse instead. As lighter fuel exhausts, pressure support weakens and cores contract. Temperature climbs, new fuel ignites, convection mixes, and neutrinos fly away. Neutrino cooling speeds the march, while radiation lakes can't keep pace. Gravity finally wins, smashing densities past nuclear values within seconds. Then shock waves and neutrino bursts forge elements in violent outsides. Numbers help. Iron sits near 8.8 megaelectronvolts per nucleon. Hydrogen to helium releases near 7 megaelectronvolts per nucleon. Past iron, the curve turns downward, making fusion a losing bet. For instance, a white dwarf endures until it approaches 1.4 solar masses. That Chandrasekhar limit marks the stability line for electron pressure support. Cross it with accretion, and the star detonates as a supernova. Another path, a core above about 2.2 solar masses, collapses. That path ends as a neutron star or as a black hole. Net result, nuclear structure dictates fates, so change follows quantized thresholds. Thread a finger along a cosmic filament, clusters hang like dew. The shape did not emerge freely, it was pruned by rules. Self-gravity pulled matter together, while random motions blurred small seeds. Meanwhile, radiation pressure at early times washed out tiny clumps. The tug between clumping and smoothing drew the cosmic web we see. In one breath, structure grows when gravity beats pressure and motion. It matters because galaxies and their star formation ride those growth curves. Growth starts from minute density contrasts in the early plasma. Photons coupled to electrons kept the gas stiff, resisting collapse. After recombination, gas decoupled, and gravity amplified remaining contrasts. Dark matter, being collisionless, started clumping earlier, guiding the scaffolding. Later, gas fell along filaments, cooled, and lit up as stars. Add feedback from supernovae plus black holes so small clumps evaporate. That sculpting halts below certain masses, set by temperature and turbulence. By the numbers, halos below about 10 to the 8 suns struggle. Photoheating during reionization kept their gas too warm to settle. Larger halos above about 10 to the 12 suns cool efficiently. Those scales explain why dwarf galaxies are faint and rare star formers. What to remember: gravity molds structure, while pressure and feedback trim the details. Hold a chip in your hand and think about limits. Physics caps how fast information can flip and how dense it packs. Uncertainty blurs timing and energy, setting a speed for distinct changes. Landauer's principle sets a minimum energy to erase 1 bit. The quantum speed limit ties energy to how fast states transform. Meanwhile, there is a ceiling on how much information fits inside. Bekenstein's bound links a region's energy and size to maximum bits. That matters because every computation, sensor, and brain obeys these ceilings. How does it play out? Energy E speeds up evolution linearly. The fastest orthogonal flip takes time near pi h bar over 2e for 1 joule devoted to computing. Flips cap near 10 to the 33 per second. Delete a bit at room temperature and you pay zeptajoules. Build a cooler machine and the energy cost falls proportionally. Yet packing bits hits the Bekenstein wall before you reach infinity. In numbers, a 1 kilogram, 1 liter object holds about 10 to the 42 bits. Earth's mass and radius allow around 10 to the 74 bits. A black hole the size of your fist saturates that information bound. Push harder, and you just make a larger horizon, not more detail. Bottom line, information is physical, so thinking speed and memory are bounded. The first line was a speed limit, and it still stands. Every constraint we touched pairs with a mechanism and a number. Those rails do not make the universe dull, they make it legible. You can see why some dreams fail, while better ones thrive. Subscribe if you want more calm, clear tour of deep space.